Well, hello, ladies and gentlemen. Let's move on. We derived last time the saturation dome by heating water isobarically. We started off with a liquid H2O. We heated it through into a saturated mixture and then up to a superheated vapor, and we developed the saturation curve and the saturation dome, if you like. So we're going to do an example today. Couple examples involving using the saturation dome to figure out the state of a particular substance. And then after we do a couple examples involving the saturation dome using the TD and the PV plot, we're going to move on to properties inside the dome. So when we have a saturated mixture, when we're inside the dome, it's a mixture of saturated liquid and vapor, how do we characterize the mixture? Well, we're going to introduce the quantity called quality. The quality of the mixture. We'll define that and derive an equation for it in due course. And then we'll do an example involving quality. So we're going to spend today on the saturation dome, and then we're going to look at calculating properties within the dome using quality. Okay? Okay, so we're going to start off with an example here. We're going to have H2O at pressure of 5 bar and a temperature of 151.9 degrees C. Very precise temperature. And we want to find the state or the phase. What is the possible state or phase of this H2O? Okay? All right, so let's get started with that. So we have a pressure 5 bar. We have a temperature of 151.9 degrees C. Okay? So I'm going to first try to find out what the state is using the TV diagram. And then we'll do the PV diagram afterwards. So here's TV. T is going to be in degrees centigrade. And specific volume will be in cubic meters per kilogram, okay? Now let me put up the saturation dome. Okay, and I'm going to put in an isobar, my 5 bar isobar. Pressure equals 5 bar. Presumably my material, my H2O, is somewhere on that isobar, a 5 bar isobar. Now, to figure out where we are, I need temperature, or I need a specific volume. I need something to lock up the horizontal or the vertical position. I know I'm on the isobar, so if I know a specific volume, or I know a temperature, in theory, I can get the state or the phase, all right? So the first thing I'm going to do is I'm going to look up the saturation temperature. I got a temperature, it's 151.9 degrees. I'm going to look up the saturation temperature of my H2O at 5 bar. So I'm going to look up Tsat at 5 bar. That's the first thing I'm going to look at, okay? So Tsat at 5 bar. Well, so if you go to your textbook here or to the notes, let me show you what we got here. So here's the PDF of your notes. So I encourage you to either get the textbook or to get the notes. And if you go to the very end of the notes, you see a bunch of tables. So index, appendix B, property tables. Don't worry about table B1 yet. It basically gives chemical formulas, molecular weights, critical temperatures and pressures for various substances. Don't worry about that. What we are interested in are these saturation tables. Saturation tables. As a function of temperature, we get boiling pressure, we get specific volume for the saturated liquid, and specific volume for the saturated vapor, and some other stuff. So these are saturation tables. Let's look at this saturation pressure table. So instead of having temperature in the first column, we got pressure in the first column. Pressures in bar. Let's see here. We are at a pressure of 5 bar. Here's 5 bar right here. The boiling temperature or saturation temperature at 5 bar is 151.9 degrees C. So Tsat at 5 bar is 151.9 degrees C. And by the way, that's also equal to our temperature. Equals T. So we're at the boiling temperature, precisely. So Tsat of 151.9 degrees C. That's also equal to T. Okay? That means we're somewhere here along the isobar. We are a saturated mixture of some kind. We could be a saturated liquid, or we could be a saturated vapor, or somewhere in between. The point is, we are some kind of saturated mixture. Saturated mixture, okay? If I was below 151, I'd be a supercooled liquid. If I was above 151.9, I'd be a superheated vapor, okay? So we are at Tsat. That means we are a saturated mixture. Let's do the same thing with the PV plot. Pressure, specific volume. Here's our dome. Here's my isotherm. Okay. Now I'm at 151.9 degrees C. I guess this pressure is in bar. Okay. So I'm somewhere on this isotherm. Somewhere on the isotherm. Now, what is the boiling pressure at 151.9 degrees C? The answer is 5 bar. Tsat at 5 bar is 151.9 degrees C, but that also means that Psat at 151.9 degrees C is 5 bar. Okay, you see that? 151.9 degrees C is the boiling temperature at 5 bar. So the boiling pressure at 151.9 degrees C is 5 bar. Another way of saying the same thing. So this is 5 bar. Psat at 151.9 is 5 bar. Okay? And that also is equal to our pressure. So Psat is also equal to P. Saturated mix. We are somewhere along this isotherm within the dome. Okay? Saturated mix. Saturated mix. Saturated mix. Okay? That's the first example. Saturated mixture. Let's do the second example. Oh, shoot. Damn. Okay, again, boiling temperature at 5 bar is 151.9 degrees C. That means we are along the isobar somewhere in the dome. This is our temperature, and it intersects with our isobar inside the dome. Therefore, we are a saturated mix. For the PV plot, pressure, specific volume, we are at 151 degrees C, and our boiling pressure at 151 is 5 bar, which is also our pressure, 5 bar. So that means we're somewhere along the isotherm within the dome, okay? Could be a saturated vapor, could be a saturated liquid, could be a mixture, okay? Some kind of mixture. Sorry about that. I always forget to turn these things back. Okay, let's do another problem. Let's do another problem. H2O. And instead of 5, tell you what, we're going to leave it at 5 bar, but we're going to crank up the temperature. 200 degrees C. Let's find the state. Here's our TV. And here is our PV plot. It's our dome. There's our dome. There we go. So we are on 5. So let me put in the isobar. So here is our isobar. 5 bar. Isobar. And again, the boiling temperature, Tsat at 5 bar is 151.9 degrees C. We got that from the previous problem. That's our boiling temperature, okay? Now we are above that. We're at T equals 200 degrees C. The intersection of my 200 degrees C isotherm and my 5 bar isobar is right there. That is the state. That is the superheated vapor region. Superheated vapor region out here to the right of the dome. So temperature, which is 200 degrees C, is greater than Tsat at 5 bar, which is 151.9 degrees C. That implies superheated vapor. We are hotter than the boiling temperature, so we are superheated vapor. We're at a higher temperature than boiling temperature, superheated vapor. Okay? Put a little box around this superheated vapor. Okay, what about the PV plot? Let me put in an isotherm. So here's my 200 degrees C isotherm. 200 degrees C isotherm. I guess I'm going to need this space. So I'm going to look up the boiling pressure at 200 degrees C. Tsat at 200 degrees C. I'm going to look that up. Let's go to our saturation tables. Okay, I want temperature here, table B2, saturation temperature table for H2O. 200 degrees C, the boiling pressure is 15.54 bar. 15.54 bar. This is in bar. Okay. Now we are at 5 bar. Intersection of the isotherm and the isobar. Isobar is horizontal, the isotherm you can see here. 200 degrees C isotherm puts me in the superheated vapor region. Superheated vapor. Mathematically, Psat, which is 15.54 bar, is greater than the pressure, which is 5 bar. Our actual pressure is below the boiling pressure, so we're in a superheated vapor. Superheated vapor. Superheated vapor. Okay? Our pressure is below the boiling pressure, superheated vapor. Our temperature is above the boiling temperature, superheated vapor. Okay? Let's do a last problem here. Let's do, PSAT, 200 degrees C, 15.54 bar. 15.54 bar. We're at 5 bar. Intersection of my 5 bar isobar and my 200 degree isotherm gives me the state, superheated vapor region. Another way of saying that is our pressure, which is 5 bar, is below the boiling pressure at 200 degrees, superheated vapor. Let's do another problem. Let's crank up the pressure to 2.5 megapascals. 2.5 megapascals. Let's crank up the pressure. So now we have a pressure and temperature, and a much higher pressure this time. Let's crank up the pressure. Crank up the pressure. Let's see here. Pressure 2.5 megapascals. And what's our temperature? Our temperature is going to be 200 degrees C again. Temperature 200 degrees C. Let's find the state. TV and PV. Pressure is going to be in bar. And temperature is going to be in degrees C. Okay? Okay, so let me put in a saturation dome. Here's my isobar. This is pressure equals 2.5 megapascals. By the way, 2.5 megapascals, let's see here, let's convert that into bar. Pressure 2.5 megapascal. Let's see, a megapascal is what? 10 to the 6 pascals. Oops. So 1 megapascal is equal to 10 to the 6 pascals. Okay? And 1 bar is equal to 10 to the 5 pascals. Okay? 1 bar is 10 to the 5 pascals. Notice the pascals cancel and the megapascals cancel. And I get 25 bar. Okay, so 2.5 megapascals is 25 bar. Let's look up the boiling temperature, or TSAT. TSAT at 25 bar. Let's look at TSAT at 25 bar. I hope I have it. We will see. Let's see here. Oops. Try to switch it off this time. Okay, saturation temperature tables, saturation pressure tables. 25 bar. I actually don't have it. I have 20 and 30. So I am simply going to take the average of these two. Let's do the simplest interpolation we can do, or right smack in the middle of the two. So let's see here. I have 233.9 plus 212.4, and I'm going to divide that by 2, and I get 223.15 degrees C. 223.15 degrees C. Okay? That's from just doing a simple interpolation. We're right smack dab in the middle between two data points. So I have 223.1 degrees C. I'm going to put an approximately equal here. Okay? So this guy is approximately 223 degrees C. Okay? 223 degrees C. Now we are below, we're below that. We are at 200 degrees C. That's our temperature. Intersection between the isobar and our isotherm puts us in the supercooled liquid region. This temperature is greater than 200 degrees C, which is our temperature. Tsat at 25 bar is greater than 200 degrees C, which is our temperature. So we are cooler than boiling. Cooler than boiling, super cooled SCl, super cooled liquid. Super cooled liquid, SCl. Super cooled liquid. Okay. Let's do the same thing on the PV plot. Here's our isotherm. So this is 200 degrees C. Let's find our boiling pressure at 200 degrees C. Let's find our boiling pressure, or Psat, at 200 degrees C. This one might be, we might be able to find this one. Let's have a look. Pressure table, saturation temperature table. 200 degrees C, 200 degrees C, 15.54 bar. .54 bar. Psat at 200 degrees C, 15.54 bar. 15.54 bar. 15.54 bar. So that means Psat at 200 degrees C, 15.54 bar. Okay? Now we are at 25 bar. We're actually at 25 bar, so this is 25 bar. That's my pressure. Intersection between our isotherm and our isobar puts us in the supercooled liquid region, SCl. Psat at 200 degrees C is less than P. Our boiling pressure is less than 25 bar, so we're super compressing it. So we got a super cooled or compressed, super cooled liquid. Okay? Okay, that's how these phase diagrams, saturation dome problems work. Okay? Put in an isotherm, you put in the saturation dome, you put in some isobars and isotherms, or isocores. You got volume here, specific volume. And you see where the intersections are, and that's where you know the state is. Okay.